This Friday morning session. The speaker is Professor Barbu from University of Iasi. The talk will be on stabilization by noise of Navier-Stokes equation.
Thank you, Marco. First of all, let me thank the organizer for inviting me here. It's a big pleasure to be first time here. And now coming in the subject of this seminar, the problem I'm considering here is not stochastic, it's a deterministic one, but which is solved by stochastic tools. More exactly, the problem is stabilization of steady-state solution to this Navier-Stokes equation in 2 or 3D. In fact, that means equilibrium solution which is given here by system 2 by using some controller, distributed controller, so put here is the right-hand side with a support in some subdomain. Is a so-called problem of internal controllability of Navier-Stokes, or in general of a PDE equation. So to stabilize a steady-state solution, in fact, putting a control here. Why to stabilize? Because in general, for the nu z0, which is the inverse of Reynolds number, this steady-state solution, which are many here, in general, it is known as a number of steady-state solution. It is finite, but generically finite. Because in general, as I said, a steady-state solution is not stable if nu 0 is small. For example, this stays hydrodynamic. Limit example of hydrodynamic is not stable. So it is turbulent. So as in automatic control theory, the problem is to eliminate instability, in this case turbulence, but putting here some controller in the right-hand side. A controller, but of course it is important to put a minimal controller. That means a controller with a support in some open set or on the boundary if it is possible. So this is the main problem of fluid dynamic theorists, in fact, how to stabilize, how to eliminate turbulence by putting some good controllers here, minimal controllers here, or on the boundary if it is possible. Okay, before going to our approach to this problem, let me briefly describe the history of this problem. So the problem is the following. If you can stabilize a steady-state solution to this equation by using some internal controller, perhaps first we should begin with controllability problem. It was conjectured by late Jacques-Louis Lyons that any equilibrium solution to Navier-Stokes equation is exactly locally controllable. But this was proved, okay, very recently, quite recently. In fact, the definitive proof is given by Emanuilov in 2000. In fact, when he proved that if we are given a steady-state solution to this equation, like here, equilibrium solution, and a certain interval 0t, we can find an internal controller which steers initial data in 0 in this time. This is the exact controllability of steady-state solution, which is a stronger property than stabilization. I want to mention that the proof of exact controllability is quite difficult because it relies on Karleman inequality, and Karleman inequality for Stokes equation, more exactly for linearization Stokes equation, are very hard. Even now, okay, in fact, you need only observability, but because Karleman inequality, even now, in fact, it is in discussion. Okay, but we have the exact controllability result for steady-state equation with internal controller. What it means internal controller? It means that you put in the right-hand side here a control of this type, mx u tx, where m is a this is a domain, this is a small subdomain O0, and m is a characteristic function of subdomain O0. That means if you put in the right hand, we can find a controller of this type such that the solution is exactly controllable. Okay, this is exact controllability problem. Our problem of stabilization, of course, if you have exact controllability, you have also stabilization. But stabilization, it is less from this point of view, but in fact, if you want to construct a feedback stabilizer, a feedback controller, this does not follow for exact controllability problem. And this problem was solved, in fact, in my paper, in fact, in SIM Koch, COC 2003. And after, in a joint paper with Trigiani in Indiana, 2004, we found that this controller can be chosen in feedback form, but finite dimensions. That means of this form, ut psi I x, I equal n, where uit are feedback, are representable by feedback. That means as a function of x. So I have exact stabilization by using a finite number of controllers. Okay. I want to say that the construction here, or here, for instance, and meantime, appear many other papers extended this result to boundary stabilization by using the same technique. There are papers by Fursikov, Raimond, and many others in recent years. It's also a paper myself and Irena Lasiecka and Trigiani, which extends this result to boundary controllability. But I want to say something here. To construct this feedback controller here, that means uit, a function fi tx, this is constructed, the feedback controller is linear, but it follows solving a Riccati infinite dimensional equation. Okay, we all work, especially people working in control theory, with infinite dimensional Riccati equation. It's a very nice instrument to stabilize infinite dimensional system. But I want to say that people, especially in fluid dynamics, are not very happy, because to solve an infinite dimensional Riccati equation, it is impossible at this moment. Finite dimensional is different, there are codes, but in infinite dimensional, if for infinite dimension, for Navier-Stokes equation dimension 2 or 3, if you take, for instance, the approximation, because, okay, how to solve? We take a approximation, finite dimensional approximation of the problem by finite dimensional spaces and solve Riccati equation on each one. It is considered that the number of the, for n, we should have always n bigger than 100 to have a good, sharp result from practical point of view. But on the other hand, if you work with this dimension, this is impossible from point of view of computational. It's not my opinion. I'm not an numerical analyst, but people from, okay, from the Center, Fluid Dynamics Center in San Diego, which are doing a lot of computation, they say, okay, it is impossible to treat Riccati equation, and not only Riccati equation, but also to solve optimal control problem associated with Navier-Stokes equation numerically, because we should take a large dimension of the space, and simply this implies if you take n greater than 1, it is something 10, I don't know, something, it is impossible anyway in this case. So this result, I'm sorry to say, because I like this deterministic stabilization result, are very nice theoretically, but numerically, okay, practically, it is impossible, in fact, to put in for Navier-Stokes equation, because you should solve, we should solve Riccati equation. So here, in fact, we propose a different approach that is stabilize this. So a different approach, which is, in fact, is to stabilize this equation, this solution, equilibrium solution here, by using an internal stochastic control, an internal noise control. And here I'm going to present which is this noise control, which is stabilizing equilibrium solution, and how to prove this in few words. Okay. So let's come back. So this is our problem, as I mentioned. So this equilibrium solution, we are doing the difference. If, of course, if you make a substitution here, the problem comes to stabilize this, the zero solution of this system. This system is not exactly Navier-Stokes. It's a so-called Navier. It is Stokes system. That means it's a perturbation of Navier-Stokes by this linear term here, this and this. Of course, you can put the system, introduce formalism, standard formalism, formalism, we can write this equation, in fact, into this form, where A is a linear operator here, okay? So A is a Stokes linear operator, so our equation can be written, let's come back, okay? Our equation can be written into this form. It is exactly this form here, where A is this operator. It is minus delta, P is the ray projector, plus this term, this is A here. Our system is this one, not control system, and we put in the right hand side a controller of this type, a feedback controller of this type, which will be constructed later, which will stabilize our system. More precisely, this Vj, it is constructed in this way. Vjt, it is a linear controller, xt is a state of the system, phi j star is a system of eigenfunction for the dual Stokes-Ausen operator, okay? Is a finite number. We'll precise the theorem after. And the main result is that this system, I'll present exactly the result, that this system is asymptotically stable in probability with high probability. Okay, which is difference, because this is a stochastic stabilization. The main difference between deterministic stabilization, this one, is the simplicity, in fact. Our feedback control is very simple. No computation at all. We should compute only some scalar product, if you would come back. No solving Riccati equation. And it is asymptotically stable in probability, with high probability, let's say, now with a certain rate gamma. So this is a big difference between Riccati-based stabilization and stochastic-based stabilization. So now let me go to presentation of the main result. Okay, so I'm considering here filter probability space, Bayesian real Brownian motion, okay? H is a space of free divergence, as in the Navier-Stokes equation. H is a space of free divergence L2 function, but we'll work in complexified space. It is better to work in complexified space for simplicity. Okay. Now, this operator A, it is exactly Stokes-Ausen operator presented before. It has a resolvent, compact resolvent. It has a finite number of eigenvalue lambda j with real lambda j less than gamma. Gamma is fixed. And of course, it is generator minus 8 is a generator of a C0 analytic semigroup. Okay. And we are doing now, we are proceeding so. So let's denote by phi j eigenfunctions of Ausen-Stokes operator, of the linear part of Navier-Stokes, which is Ausen-Stokes operator. It is we have fixed n. N is a number of eigenvalue with real lambda j less than n. Phi j eigenfunction considers the space generated, finite dimensional space generated by phi j. And we are doing here the composition of the operator A. Is this the composition? Is a linear part, Pn is a projector, that algebraic cells. AS is a coprojector, I minus Pn is coprojector. Then both spaces, both operator AU and AS, leave invariant the space XU and its complement. The spectrum of AU consists of lambda j with real lambda j less than n. The spectrum of AS consists of lambda j, real lambda j. Yes?
Can you remind me again what is A?
Yeah.
Because I've seen some.
Yeah, the operator, okay. The operator A is this one. Operator A is this one. This is operator A, is this one. This
so the A has this perturbation.
Yes, A, it is delta, P delta. A0 is a perturbation which comes from steady state solutions. That means is a perturbation which comes from this part here. A0 is this part, this, and and this. This is A0, projection, reprojection of this. A perturbation which is due to presence of steady state solution.
Is it?
It's a so-called Stokes-Olsen operator.
But is it? It's not self-adjoint, yes.
No, no, of course. Oh, self-adjoint is a very simple problem. But still, it has a compact resolvent, so it has a finite number of eigenvalue less than a certain gamma with real part less than gamma, and so on. So it behaves very, very well. It's also generator of analytic semigroup. Okay. This is, okay. So you are doing a decomposition of this A into parts, finite dimensional parts. That means it's a space generated by phi j eigenfunctions with real lambda j less than gamma, and the rest which is infinite dimensional AS. It should be seen that E minus ST is exponentially stable. The infinite dimensional part is asymptotic, it is exponentially stable. Why? Because it's a famous gross logarithmic property. The spectrum, it is in real lambda grows to gamma, and it is analytic semigroup. So for AS it is good, but AU, which is finite dimensional, not. Okay. Now let's go. Okay, this is, we are considering also a joint. Okay, so phi j star represent the eigenfunction for the adjoint operator, A star. Of course, we have the same multiplicities. The main assumption we are doing here, it is the following. Assumption A1, all eigenvalue lambda j are semi-simple. What this exactly means? For each lambda j, eigenvalue, an eigenvalue is said to be semi-simple. Its algebraic multiplicity coincides with geometric multiplicity. That means, in this case, you are infinite dimensional, that the corresponding Jordan form is diagonal. So the matrix is a diagonal. So each lambda j has not so-called generalized eigenfunction or eigenvector, only simple. Okay, that means that resolvent only simple poles. This exactly means. It is an assumption. It's not absolutely necessary, but simplify. Anyway, it is generic. It can be proved, but it simplifies. So working with this assumption, okay, one of the main tools, in fact, we should know this lemma, that the system phi 1, that the system adjoint, that the eigenfunction associated, this finite number of eigenfunctions associated with A star are linearly independent on our domain. We are considering a subdomain O0, like here, a subdomain. And it can be proved that this system is linearly independent on L2 O0. I want to precise this. Phi 1 star, phi 2, phi n, of course, it is independent in the whole domain. But it is a deep result to prove that this system is linearly independent on every subdomain. This is quite a hard result because it realizes it is related to so-called unicontinuation problem. I want to remind the following. If you have a eigenfunction for Stokes operator or Olsen-Stokes operator, if this eigenfunction is 0 on subdomain, it is 0 everywhere, as happens for elliptic equation, for eigenfunction elliptic equation. It's not trivial, however, to be proved this. But this is something more, that if this system is linearly independent of L2O0. Okay, the proof is not immediate. The proof of this one, okay, not in the paper we gave the proof, relates on the Hermander-Karlman inequality. In fact, we reduce in 2 dimension or 3 dimension this, using vorticities, this Navier-Stokes linear equation to a fourth order elliptic equation, and use one of the Hermander unicontinuation inequality. In fact, to prove this one. Anyway, this is an important fact because we cannot have internal stabilization without proving unicontinuation, as we cannot prove exact controllability without proving first Karlman inequality. So behind each stabilization result, internal stabilization result, it is a unicontinuation result, and this result is here. The system is linearly independent of O0. With this property here, we are constructing our feedback controller. Our feedback controller, that means stochastic feedback controller, is this one. We put in the right-hand side this feedback controller. This is a scalar product in H, phi j star as the eigenfunctions or associated dual eigenfunction. P is the ray projector, eta is a real number will be fixed after, and phi j, which is phi j? Phi j will be precise later. Anyway, the system is equivalent to this one. We can write, if you get rid of the projector, we get this closed loop system. So it is, we have this Navier-Stokes, we put in the right-hand side, this noise. In fact, it is a noise. You put here the noise, and m. M is a characteristic function associated with this subdomain O0. So we have a stochastic control in the right-hand side with a support in O0 arbitrary, and the main result we'll prove is that this xt in probability goes to 0 on a certain domain. This is the result. And precisely, I'll give the theorem immediately, which is this O0, this phi g. This phi g here is constructed as follows, is given by this phi j. It is a linear combination of dual eigenfunctions, where alpha Lj is computed from this system. Because the system I precised before is independent, this gram, in fact, matrix, it is not singular, so it is possible to find a unique phi j under this form. So it's a linear combination. And now let's formulate the result. The result is the theorem that if eta is bigger than some quantity, lambda j are eigenvalues, find a number of eigenvalues, and for each x in the domain of A1, 4, with x1, 4, this is a norm in dA less than c star, there, and on a set omega star x with a probability greater than this, it follows that xt is going exponentially to 0 as t to infinity. So which is exactly the result? Exactly the result is the following, that our closed loop system constructed before, the solution of closed loop system constructed before, is going to 0 on this set, omega x star, where probability of this set is greater than this one. In any way, it follows that, for instance, that a consequence is this one, that this, if x1, 4, it is less than rho 0 a constant, this set has a probability, this is greater than this one. So in particular, it follows if you are taking initial data sufficiently small, this probability is close to 1. So this is the result. We do not have, okay, we are not able to prove. We do not have stabilization for all omega, that means almost everywhere in omega, but on a set of sufficiently great probability if initial data it is small. In linear case, that means if you want to stabilize a linear system by the same controller, we have everywhere, almost everywhere. So this is the result, that our feedback controller stabilize our system with probability greater than this, like here, this one, if initial data, it is less than rho 0. Yeah?
One more question, which results
Yeah.
from the fact that I missed. Again, what is the capital N?
Capital N is a number of eigenvalue. Yes, capital N is a number of eigenvalue with the property the real lambda is less than n, less than gamma. We have fixed gamma. We have a finite number of eigenvalue with all real j is less than gamma for all j equal 1 n. And with this n fixed, we have, as I mentioned before, that we have with this n fixed, yeah, we have that limit e gamma t over 4, it exponential xt goes to 0 on this set. Yeah. Yeah?
Sorry, same kind of stupid question. I apologize.
Yeah,
I
please.
can't. What was eta again?
Excuse me?
Eta.
Eta, it is an arbitrary. I come back to the construction.
Right.
The construction is this. So our system is the following. It's this one.
Okay,
We
right.
put here eta.
Fine.
For a moment, it's arbitrary. And this is saying that for eta big enough, It's never mind if it is positive or negative.
Yeah, I forgot where
For
I
eta
was.
big enough, this is stabilizing the system. Yeah, in fact, this is the result. Okay.
So intuitively, it means that you have your stable solution.
We have a x
stationary
here.
solution.
Yeah, let me put it this way. In particular, if you come back to our stationary solution x minus xe, this means that this feedback controller, this one exactly, the x minus xa, is stabilizing xe, this guy. So x minus xe goes exponentially to 0 on this set. Yes, coming back to xe. Sure. Sure. So as I mentioned before, how simple it is to construct and to implement the system. So it is quite simple. So it is simple. You compute phi j is an algebraic problem, phi j star, and of course this scalar problem. Okay, here is a problem. Yes?
Are the people in the computational people in San Diego happy with this now?
We'll see. I don't know. The problem now. It is only one problem here. How robust is this control? Because people fluidist, and not only fluidist theory, it is people working in control theory. In fact, important is not to find a stabilizable controller, but to be so robust. That means a modification is it preserves its stabilization property if you modify the system. Okay. In general, controller constructed by Riccati-based equation are robust. It's normal to be so. Also, this is robust. And why it is robust? Because look here, if you're modifying here, what means robust? That means if you're modifying, okay, or you have we cannot compute exactly steady state solution, this still remains stabilizable. This is correct because it is constructed with the construction depends on the spectrum of the operator A, and the spectrum, it is continuous. In fact, you have a stability of the spectrum with small. So this is robust, in fact. But of course, a precise analysis should be done here because it's not enough to say, okay, it is robust. There are some people in control theory that have automaticians have a very precise criteria here. But roughly speaking, we can say it is robust because it still remains stabilizable if you modify. Yeah. A few words about the proof. Okay. The proof. The idea of the proof is the following. In fact, coming back to our system here, I didn't say this is a stochastic equation. In fact, is that it has a solution. We have taken here dimension 2. What we have taken dimension 2? To have global existence for this equation. But it's not a problem here because, as mentioned, in fact, Dr. Kim, I remember in the first, here we are working with initial data in a neighborhood of the origin. So we still have, and this follows also from our proof, we still have a solution, not everywhere, on a probability set with a sufficient big probability. So it's not a problem. This still works in 3 dimensions. 3 dimensions, but only for simplicity we have taken t equal to. No, because in fact we are working here with solutions starting from small data. So small data, so also in, it follows in fact from the proof that, so this works also in 3D. Okay. Now, which is a proof. The idea of the proof is to transform this equation, which is a stochastic, it has solution of course, with a stochastic equation in a deterministic one. And we should use the fact that our controller is finite dimensional. If you have this controller is finite dimensional, we can equivalently write this equation as a deterministic equation, randomly deterministic equation. This is our great advantage here, because we have chosen a controller, which is stochastic controller, which is finite dimensional, we can transform in deterministic equation. Let's do this. Okay? So, this is a transformation. If I was in this transformation yt minus bg gamma j, where gamma j is this operator, it is described here, okay? This equation becomes this. This is a deterministic stochastic, this is a deterministic random equation, where gamma j squared is as this operator here. And this is a linear part, and this is a nonlinear part. So we have a semi-linear deterministic equation for each omega. Let's go further. Okay. And xt can be recuperated from y from this formula. Okay. Now, we denote the linear part, this operator, by a gamma here. As the first result is the linear part is asymptotically stable. This is the result. A gamma, this one, is asymptotically stable, exponentially asymptotically stable, for eta big enough. And here is a proof. It is not quite, this is a lemma. In fact, A minus gamma t, that means the linear part of our system is asymptotically stable, which is a proof. Well, the proof is the following. You have the system. We are doing a decomposition. We decompose the system A gamma, which has a spectrum we have seen before, in this way. In fact, A. We decompose A. We decompose A into part. It is, okay. This is a finite dimensional part, remember. Why AU is a finite dimensional part, is a projection of A on the, let's say, unstable spectrum. And AS is this operator, which is asymptotically stable. So this is finite dimensional operator. This is infinite dimensional operator. But this one, AS, has exponentially decay. Okay, let's treat the first one. The first one is a very simple one. The first one can be written to this form. Can be written in component, goes to component. The first is this operator, is this system here, which more exactly is this one. Okay, but this is a finite dimension, is an equation for eta big enough. Of course, yj goes to 0 exponentially, so it's not problem. So this is a proof. As regards the second part, as I mentioned, this one, because AS has exponential decay, here we have put something which is exponential decay, it follows ys is the same thing. So the linear part of our system is stable for eta big enough. So no problem here. Everywhere in omega, that means almost everywhere in probability. No. The problem now, in more, we have something also, we have something more. We have also a better estimate, in fact, of this time, this norm of this operator, it is less than this. Okay. Now we are going to consider to treat the nonlinear system. That means we have this coming back. So our system, remember, is this one. Okay, our system is this one. This has a nonlinear part. B is an inertial term in Navier-Stokes. This is linear part. We have seen that this linear part is asymptotically stable. But we appear here a nonlinear quadratic term. So we must prove, in fact, that the system as a whole is convergent to 0 with rate minus gamma for x in a neighborhood. Okay, how to treat? So we should treat this one. Okay, here we should use standard estimates for inertial term in Navier-Stokes equation, Laplacian scale estimates, so-called. Okay. So coming back, and here we are doing, it's exactly what we are doing here. In fact, we are computing this B. The problem is here that arises this term, BAG, so there's some extra term, BY standard Navier-Stokes term, plus extra term which involves in say computation is beta j. Okay, after computation, we arrive to this system. So our system can be written to this form, where j has this form. By is a standard inertial term plus theta. Theta is that one has, however, an estimate of this time for theta. Estimating theta with a norm of d alpha arise, of course, this is not independent in omega, I want to say. So we should prove that the system, the solution of the system goes to 0. To do this, we transform the system, okay, because we need in fact to prove that E gamma t, y goes to 0. We transform this and write the system into this form, this integral equation. Well, the best way to prove that the solution zeta of this system is going to 0 is to prove that this integral equation has a solution zeta in L2. This is the best way. Other way it is difficult. You cannot estimate here, simply multiply by zeta and so on. So the best way, in fact, the idea comes from a joint paper with Irena Lastielska and Trigiani when we were doing the same thing for deterministic equations. So we'll prove that this equation here has a solution, ST is minus gamma. It is the exact operator generated by this one. So it proves that this has a solution L to 0 infinite using standard fixed point argument. But it's not so easy, and the result is the following. In fact, that there is a subset omega x with a probability greater than this term here, such that for x 1/4 less than this c, this equation has a unique solution, zeta in c of this form. We can say the row zeta is in L2, 0, infinity, R3/4. Okay, if you have a solution zeta in L2, 0, infinity, this is already a type of convergence to 0, but we'll prove in fact that is convergent. Okay, the idea is not idea is a old one. The tool is to use standard Banach's fixed-point theorem to this equation here, zeta st plus n zeta, where n zeta is this operator. So we should find an invariant set for this operator, and to prove that on this invariant set, this operator is a contraction. That is exactly is doing here with some technicalities. In fact, we should go some estimates on n zeta. What is difficulty here? The difficulty here is that all the estimate depends on omega, because in G arise this term omega. In fact, it is E gamma T and so on. So all the estimates should be done here. Let's go a little bit. Okay. So finally, we get this estimate. We get lambda zeta, which is the right-hand side of the operator we have, is estimated by this one, where this supremum 1t is 1 plus mu omega. So we get an estimate for lambda zeta for right-hand side, but depends on omega. And this is a problem. Here, in order to estimate the right-hand side, we use this lemma. Okay, because we need some estimate on the beta, on the Brownian motion. So, okay, it is after we use it quite a study, but it is can be found in books. Okay, this lemma, and this allows us to prove, in fact, finally to prove that this operator n on a set of this form where a omega is determined, leave invariant this set U omega, and is a contraction here, where on a set of the probability greater than that I said. So this means that we have a solution for our problem. Okay, this is exactly the item here, omega. We have a solution is a contraction here. So the result is on this set we have a solution on a set omega x. We have with a probability bigger than this one. We have a unique solution zeta for our operator. It remains to be proven that y goes to 0, but this is quite immediately. In fact, this is this lemma. So we prove that y. So we prove that yt is going to 0 exponential. Now coming back to x is determined by this one. We should work once again to recuperate this to see exactly. And we find that x, in fact, is our state exponentially. Have an estimate of this type. That means xt e gamma t over 4. It is bounded or goes to 0 on a set of this probability. So we succeed to prove that our system, which is a nonlinear system, has a solution which goes exponentially to 0 on a set of this type. It is exactly a set with a probability which could be close of 1, if of course eta depends of eta and depends of course. So okay, this is more precisely on a set of this type, probability on the set of this type, we have this result. So this is in fact the main result, that our noise controller, internal noise controller on an arbitrary subset, stabilize steady state solution with probability this one. This is probability stabilizes with a given rate. And the controller, yes.
About this given rate, can you actually you have some estimate on the rate from above?
The rate is given. If you are given the rate, we obtain the n, the number, the dimension of the controller. And
okay,
eta is our disposition, in fact.
Okay, I'll discuss rate.
Yes, yeah. Yeah. So we can stabilize with an arbitrary rate if you afford a larger controller. Okay. So we should choose between. Yeah. Now, this is stabilization. Let me say a few words about boundary stabilization or boundary stabilization in noise. Okay, internal stabilization, it is important, but fluidist people consider that more important is boundary stabilization because, in fact, stabilize system, Navier-Stokes system from the interior, that means, in fact, to put pressure. The controller is a force, is a field force, in fact, in this case, so put pressure, in fact, in the interior, but this is, okay, we can do this, but it's more important to find a boundary controller to stabilize the system. The boundary controller, even in deterministic case, for Navier-Stokes equation, is still an open problem. In what sense? We can stabilize Navier-Stokes equation in this moment by using tangential controller. This is done is recently, and also I saw no paper and some paper as I made by Fursikov, by Raymond, myself, and Irena Lasiecka and Trijan and so on. But it's important, not tangential. Why tangential? It's much more easier to construct tangential controller because this corresponds, in fact, to a controller which is a trace of an element of the space H. That means which is tangential and has free divergence. More difficult, if not impossible, because so far we don't know, it is to control using normal controller. Normal controller. Here, okay, the problem so far is solved only for periodic flow in channel. Periodic flow in channel. That means we have a two-dimensional channel, something like this, Let's say x, 0, x, y, 0, 1, 2 walls. We have a fluid here, and we assume that it's periodic. Okay, people work with periodic fluid, so this is not a realistic, because it is much more, it is easier to work with periodic flow, in fact. And periodic flow, especially in channel, it is also applied people work quite frequently with periodic flow, in fact. So here we are considering this problem here from stochastic point of view. So we are considering this system, U and V, as a component of the fluid. In this case, this is a Navier-Stokes system. In fact, we are putting U in 0 and 1 Dirichlet boundary condition, and we control V. Normal component is 0 on this wall, and we are taking V1 equal V star on the wall, superior wall 1. And we want to control, not to control, to stabilize the system choosing a V star, a feedback controller V star. That means we want to stabilize this fluid. This is what means exactly a steady state flow. A steady state flow for the system, it is interesting, but has not many. The only, it is, okay, this fluid has a family of steady flow of this form. The parabolic profile. This is a steady state. This parabolic profile where C is positive or negative. So our intention here is stabilize this profile. We precise this, only to precise, by using a controller for this normal controller in V. As I mentioned before, this controller is this one, so come back. We want to find V star such that this parabolic flow I mentioned before is stabilizable. No? Okay, what we are doing in this case? We are not able to stabilize the nonlinear, but we are able to stabilize linearization, in fact. Well, people, again, I should refer to people in automatic control theory. They consider if they are doing stabilization for linearization, it is okay. Well, it's not always okay, it's not always true, but okay, so let's do ourselves. So we are going to stabilize, in fact, linearization of the system, which is written here. No nonlinear part, U is this function here, and of course we have boundary condition here. This is a free boundary condition, free vector field. Here V is, okay, not. Periodic condition in U, you can see U is periodic and V is periodic in X. Here is no 1, X plus P. We are considering a periodic flow in X. Now this flow, it is periodic along this axis in X now. And Dirichlet and respectively Dirichlet condition to the, okay. Why it is simpler to work with this one? Because in this case you can decompose the problem. We can write on component because we are taking, in fact, Fourier representation of solution. That means V star is representing in this form, V star our controller here, also V and V car. And this system can be written in component, Fourier component into this form, an infinite dimensional system. Can be written in this form, in UK, VK. VK star, this time a function of t in this case. So we are writing the system as an infinite system in component, which is a controller in this case. The system can be written, we should get rid of P. In this case, we should get rid of P. And the system in VK can be written to this form, which is AK. AK is this operator, FK. This is second order operator with a homogeneous boundary condition. FK is fourth order operator here. So our system is this one, and which is this decay. This decay is a so-called Dirichlet map. Dirichlet map associated with our boundary control problem. Now it is known that you have an optimal, if you have a control problem with control on the boundary, we can we can eliminate, homogenize the condition, but using this Dirichlet map associated with this one, but which arises in this form. But this operator is not bounded in this case. It is an extension of our operator. So we have this system. So our problem now, it is stabilize the system. That means phi Vk star in feedback 4, such that Vk goes exponentially to 0. What is the problem? Well, apparently you have an infinite dimensional system here. But in fact, if you write AK into this form, okay, it turns out that this operator AK is stable is unstable only for a finite number of modes K. So only for a number of K, this is unstable. So it is enough to stabilize the system for K less than some M, because in the rest it is stable. So we should work with the system here. Okay, I simply construct which is a feedback controller in this case. I indicate it is a feedback controller, because we find also in this case a feedback controller for VK star here, and this is a following. Okay, is this feedback controller is this one. The result is this one, in fact. Okay, feedback controller is this one. VK star has this form. It is exactly this form. Beta J, it is Brownian noise. No? But of course, here we should take a complex Brownian motion. It's a problem, in fact, so Bj is not real, but is a complex Brownian motion. And computation shows that indeed, proceeding as before, that this Vk star, putting into equation, which is in feedback form, for eta large enough, in fact, for eta large enough, is a stabilizing for our equation. In fact, is the next result, which is here, that V, where V is of this form, where Vk is a solution to this equation, or Vk star is precise as before, is stabilizing exponentially V. Okay, if it is stabilizing the normal component, of course it is stabilizing also tangential components, so it is stabilizing globally. So this time we have a system with boundary, a stochastic system with boundary controller. Okay, but it has a solution, in fact, because it is quite simple. In fact, for instance, in the book by Giuseppe and Jerry Zapchik, okay, is an example of this type. No, exactly of this type as precise before. No, it is simpler, in fact, construction. So this feedback, in fact, acts on, and this time it is almost everywhere, because the system is linear. So this is stabilizing with probability 1 exponentially our system. No. Okay, so roughly speaking, that's exactly I wanted to present here. Now, this, let's say, a stochastic tool to stabilize Navier-Stokes equation. The problem, I begin with I'll finish with the beginning. In fact, the problem of stabilization of steady-state solution is crucial. In fact, okay, mathematicians are most interested in existence and uniquences for dimension 3. Okay, it's a very big and unsolvable, perhaps, mathematical problem. But fluidists are more interested to eliminate turbulence. That means how to eliminate turbulence by using simple controller. And especially in the case when this nu, that means Rayleigh 1 over Rayleigh number, it is small. It is small. Of course, coming back to this result here, this result here, okay, is no condition. In fact, this is nu, it is viscosity term. Now, our feedback controller, stochastic, works for each nu. No condition about nu. But if nu is large, we should take a larger number of controller effect, but still remain finite dimension. But there's no condition about nu. It works under all conditions, in fact. And likely, this control system, like in previous case, I think that is simpler to implement. So I was told by physicists it's not a problem to implement noise in system. Okay, perhaps it is true. Okay. I want to say something more, because perhaps I should say something about references about noise stabilization. This method is not new. Stabilization by noise of differential equation is well known. It was firstly used for ODE equation, for maybe 25, maybe more. And after also, I have here from some references, in fact, and after for PDE equation, but not in this context, of course. And because here we are combined, in fact, stochastic stabilization with spectral stabilization is this argument here. But also Professor Martini remembers it has paper about some works about this one. So it was used before, in fact, for ODE equation, but not in this way. That means here we reduce noise stabilization of PDE to noise stabilization of ODE. It's much more simpler. I remember, for instance, in a talk by Dr. Kim, in fact, that he presented something similar, but it was in a different context, in fact, because it is another possibility to get noise stabilization. It use, in fact, Ito formula with singular Ito function, in fact, but it is much more. Okay. So there is a literature already in ODE, already on PDE, especially for some spatial PDE, and in fact, I was inspired by the literature existing. But the problem here, as we presented, by me it is new. Okay, so I thank you for
There are comments, questions?
yeah.
In the first part, if you
Yeah.
first part of your talk,
Yeah.
if you replace, or do you have a feeling if you replace the noise in the controller by increment of bounded variation, so let's say dt, then it should not work.
Yeah, I'm sure that it not
Yeah.
work. It does not work
Okay.
because
Okay.
yeah.
So my question is, now you can interpolate between bounded variation and quadratic variation. So do you have a feeling what is the critical exponent?
No. In fact, my first approach was by using this one was standard one, in fact, to use Ito formula, in fact, in finite dimensional. So in this case, Ito formula, okay, permit you to stabilize. If you do not have a noise, that means that you say Brownian
I don't
motion.
think it is the noise which is the stabilizing effect.
Is a noise, yes, exactly.
Yeah, but my statement is it is the variation of the increment. So because the Brownian increment has
I
a
understand.
high, it's
Yeah.
Euler continuous or something like that. So this is the effect which draws the solution into the steady state.
Maybe. I don't know. I think that. didn't follow this.
Me the same. I had the same question in a sense. In practice, it is difficult to realize approximations of Ito noise. If you use Stratonovich,
Yes, because you can get different form of integer, Stratonovich or so on.
if you write Stratonovich, perhaps your theory changes.
Yeah, perhaps.
Because there are
Perhaps.
corrections which.
But in practice, we do not compute here. In practice, I make doing an observation X and put a noise in the system. It's not. We should not. Here, we should not approximate anything. In fact, except phi j star, these eigenfunctions for the system, for the deterministic system.
If you want to realize physically the system,
Physically,
approximate the noise by some real noise. And are in trouble with
you should be seeing exactly how you are doing, but it seems to me that you can simply produce noise without approximating it as. But yeah, perhaps. So,
Other questions? No, thank you.
thank you.